Hello folks, welcome to this lecture short. I'm Jason Chang. This lecture is about diagramming arguments, and one of the things we'll see is that diagramming arguments is an important skill when trying to dissect and analyze a passage that contains an argument. Fortunately, the basic idea of diagramming arguments is very straightforward and not difficult to understand. Where it gets a little bit more difficult is when the passage that contains the argument is a little bit lengthier and contains claims that are not necessarily relevant to the argument. So this ability or skill of diagramming arguments is actually developed through practice. So what we'll do in class is practice exercises in which we'll cultivate your ability to diagram both longer and shorter passages that contain arguments. But this lecture's goal actually is not very ambitious. Essentially, I want to just give a little bit of background and a definition of diagramming arguments and to show you how it's done. And I'll give you plenty of examples just to illustrate how to diagram different types of passages with arguments. And then we'll talk about the different ways in which premises can support a conclusion and the way in which we should depict these differences, these different types of support in diagrams. So just to start off with some of the basics of diagramming arguments in terms of what diagramming arguments involves and why it's important. And as I said earlier, fortunately, the basic idea of diagramming arguments is quite simple and straightforward. Where it gets a little bit more complicated is when the passages we're diagramming are quite lengthy. But when we're diagramming arguments, essentially what we're doing is we are representing an argument in a diagram or picture. And that means depicting the premises, the conclusion, as well as the inferences or the logical moves from the premises to the conclusion. And I'll show you how to do this in the next slide. But before we do that, just a little bit about the purpose of diagramming. Essentially, what we're doing is we're trying to make it easier on ourselves to understand and evaluate the argument in front of us. As you probably know, if you're reading an argument in a publication, there's a lot of information that might not be relevant to the argument itself. So there might be, for example, background information or editorial remarks, or digressions, or subsidiary points, and parenthetical remarks, and so on. But what we want to do with diagramming arguments is we want to expose the bare bones, that is the premises, the conclusion, and the inferences for the purposes of understanding and evaluating the argument itself. Okay, so let's just start off with the basic information that you'll need in order to diagram arguments. And the good news is once you have this information, along with the different types of support that we'll talk about later, you'll be able to diagram, at least in theory, any argument that you see. So as I said in the previous slide, when we're diagramming an argument, we're trying to represent the argument in a diagram or a picture where we represent the premises as well as the inference. In the premises and the conclusion, what we're doing is we're representing them as encircled numbers. And this will require labeling each claim in the argument with numbers so that we can use the numbers in our diagram. The inferences, or the moves from a claim to another claim, are represented by arrows. So let's just take an example. So here we have an argument that consists of two claims. The premise is John has sprained his ankle, and the conclusion is John will not win the marathon, right? So plain and simply, to diagram this, what we do is we represent the premises and the conclusion as encircled numbers. So 1 represents the premise, and 2 represents the conclusion. And then we represent the inference from premise to conclusion with an arrow right here. So this represents 1, so 2, or 1, therefore 2, or 1 gives support for 2. Okay, so what I've done here is I've taken the same argument as the previous slide, except I added another premise here, which is 2. John has food poisoning. So here this reads John has a sprained ankle and John has food poisoning as the premises. Therefore, it follows that John will not win the marathon. Right? That's actually a pretty persuasive argument, that he probably won't win the marathon if he has food poisoning and has a sprained ankle. But anyway, we saw in the previous slide that the simpler version of this argument was 1, arrow 2. What we're going to have to do here is add this second premise in red. So the diagram will look something like this, where we have the encircled numbers 1, 2, and 3 representing the premises and the conclusion respectively, and then we have the arrows representing the inference from the premises to the conclusion. So this diagram suggests that 1 supports 3, or 1 so 3, and in addition 2 supports 3, or 2 so 3. So here, yet again, I've taken the same argument from the previous slide and I've added an extra premise here. So the extra premise is that John also just broke up with his girlfriend, which is even more reason to think that John will not perform well at the marathon. So here, we're going to have to add that extra premise. So now we have 3 premises supporting the conclusion, and the diagram, as you probably have guessed already, looks something like this, where the numbers 1, 2, and 3 represent the premises, and the number 4 represents the conclusion. So this diagram shows that 1 supports 4, 2 supports 4, and 3 supports 4. So, yeah, we have 3 premises supporting 1 conclusion. Okay, so just to change things up a little bit, here if you read this argument, John is lactose intolerant, so John should avoid cheesecake. That is why John should not go to Cheesecake Factory. Okay, so here you'll actually notice that there's a sub-argument here, which I have highlighted in blue. The sub-argument actually the sub-argument is such that 1 supports 2, and then once 2 is established, that supports 3. So I'm going to just represent the move from 2 to 3 first. So this right here shows that John should avoid cheesecake, which is 2. Therefore, John should not go to the Cheesecake Factory. But what we need to do here is represent this sub-argument beforehand. So before we actually can use 2, we have to establish 2 through a sub-argument. So the way we're going to depict that in the diagram simply is as follows. So the sub-argument right here is 1, so 2 or 1 gives support for 2, and then once we have 2, we could use 2 to arrive at 3. Okay, so here's another example with a sub-argument, and this time I've actually used the same argument with John not winning the marathon as the conclusion. But what I've done is I've added the sub-argument with in adding claim 5, which is not depicted in this diagram yet. But this diagram on the right-hand side actually simply depicts the original argument 1 through 4, which, as a reminder, the conclusion is John will not win the marathon because premise 1, John has a sprained ankle. Premise 2, John has food poisoning, and premise 3, John broke up with his girlfriend. Okay, but here there is a sub-argument from 5 to 1. So this premise over here is being supported by another premise, premise 5, and the move from 5 to 1 is the sub-argument. So the way we're going to depict this in the diagram, you probably guessed already, is ta-da! So 5 supports 1. This right here is the sub-argument. Then once we have 1, it goes together with 2 and 3 in order to support 4. Okay, so just to make things a little bit more complicated, and as you'll see, as we get into more difficult and longer passages, the diagrams actually will be quite expansive. So here, on the right-hand side, I have the same argument as I did in the previous slide with the sub-argument and all. So John landed awkwardly on his ankle, so John has a sprained ankle. But what I've done is I've added another sub-argument for 5 here, as well as another one for 2. So you might wonder, is it possible to have more than one sub-argument, or is it possible to have a sub-argument? And the answer is yes, it is. So I just want to show you how to depict that in a diagram. So once again, here we have our original argument from the previous slide. Let's start off by representing this this sub-argument, so the sub-argument that contains 6 as a premise and then 5 as a conclusion or a sub-conclusion. So John was not careful when playing basketball, so 5, John landed awkwardly on his ankle when playing basketball. That in our picture or diagram will be represented as follows. So here, as you can see, we actually have 2 sub-arguments. The sub-argument that establishes 5 as a sub-conclusion, and then a sub-argument that establishes 1 as a sub-conclusion. And once we have 1, we could use it as a premise to support our ultimate conclusion, which is 4. All right, so the next sub-argument, which I've represented here, here it looks like 7 in a sub-argument is a premise, and 2 in the sub-argument is the sub-conclusion. So the way in which we're going to represent that sub-argument is here, 7 to 2, and here's the sub-argument. So once we have 2, we can use it to support the ultimate conclusion, which is 4. So it looks like here we have 1, 2, 3 sub-arguments. And if you want to know if we could actually have more sub-arguments than 3, the answer is yes, we can. In fact, we'll probably see arguments later on in which we have several, more than 4 sub-arguments. Okay, so the previous slide was meant to just introduce you to the basic idea of diagramming arguments, as well as give you specific examples of how diagramming arguments works. And hopefully by now you're comfortable and familiar with diagramming at least shorter passages that contain arguments, as well as passages where the arguments contain 1 or more sub-arguments. And we'll practice this more in class, but I do want to move on to the types of support, or the ways in which premises can support a conclusion. And this is the next thing you'll need to know in order to be able to diagram, in theory at least, any argument in a passage. The good news is once you know this, specifically 2 types of support, and you couple that with the diagramming containing encircled numbers and inferences represented as arrows, you'll know everything you need to know in order to diagram any argument. So there are 2 different major types of support, or ways in which premises can support the conclusion. In the next couple slides, I'll talk about the first type of support called convergent support, and then in the subsequent slides, I'll get into the second major type of support, which is called linked support. But let's just start off in our discussion of convergent support with the argument that we've been dealing with in the previous slide. So the argument that John will not win the marathon. And as we saw, this is represented in a diagram as follows, with 3 premises and 1 conclusion. Now here I want you to notice that each premise supports or gives reason for the conclusion independently. In other words, 1, John has a sprained ankle. That by itself gives reason to think that John will not win the marathon. Even if we were to completely eliminate 2 and 3 and we just had 1, so 4, 1 would still give reason for 4. And the same thing can be said for 2 and 3, right? So even if we eliminated 1 and 3, the fact that John has food poisoning by itself gives reason for 4. John will not win the marathon. And likewise for 3. John just broke up with his girlfriend. Even if we were to eliminate 2 and 1, 3 would still give reason for 4. So in other words, more generally, each premise supports the conclusion independently, by itself. So 1 supports the conclusion independently by itself, 2 by itself, 3 by itself. It just so happens that these 3 premises converge onto the same conclusion, but each by itself supports the conclusion. So this is called convergent support. Convergent support is when you have premises that support the conclusion by themselves or independently. So actually I should have said at the end of the previous slide that convergent support is when the premises support the conclusion independently but happen to converge onto the same conclusion. But hopefully you picked that up already. But here's just another example of convergent support. So here we have 2 premises and 1 conclusion. War leads to deaths, and war costs billions of dollars. Therefore, this should be a period, not a comma, but nonetheless, therefore, 3, we should not go to war. So this is a convergent support in which we have two premises converging onto the same conclusion. But once again, you'll notice that each premise by itself, independently, supports 3, the conclusion. Right? War leads to death by itself supports the conclusion, and 2, war costs billions of dollars by itself, even if we were to eliminate 1, supports the conclusion. So once again, we have convergent support. Now, some people sometimes ask, how many premises can make up a convergent support, and the answer is 2 or more. So you could have 2 premises that make up a convergent support for a conclusion, or you could have 200 premises that make up a convergent support for a conclusion. Okay, so before I get into the second type of major support, or linked support, I just want to expand on what I said earlier about convergent support and how many premises are needed in order to constitute a convergent support. And I said either you could have as few as 2 or as many as, well, I guess it's infinite, right? But what I want to add here is that typically speaking, an argument that uses convergent support, the more premises that are provided that converge onto the conclusion, the stronger the argument. So in other words, an argument that has 10 premises that converge onto the same conclusion is probably a stronger argument than an argument that simply has 2 premises that converge onto the same conclusion. Okay, but nonetheless, let's get into the second type of major support, which is called linked support. And linked support is depicted, as we'll see, a little bit differently in a diagram than convergent support. That is, we're going to have to add some extra visuals or pictures or symbols in order to depict linked support. So on the left-hand side, you have an argument, and this is actually depicting the law of transitivity, where A equals B and B equals C, therefore A equals C. Now, if we were to interpret this as an argument, we would, of course, say that 1 and 2 are the premises and 3 is the conclusion. Right? Now, I want you to notice something about this argument. In this argument, in order to get to the conclusion, you need both 1 and 2 together, right? Unlike with convergent support here, there's no way in which we could get to 3 simply by 1. A equals B, therefore A equals C is just a non sequitur, or it's a the 3 simply doesn't follow from 1. The same thing with 2, right? B equals C does not lead us to 3. It's only when we combine 1 and 2 together that we can infer 3. So 1 and 2 make up what's called a linked support for 3. In other words, the premises need to be joined together to support the conclusion. Unlike convergent support, with linked support, each premise on its own does not support the conclusion. So, you might ask, how do we represent a linked support in a diagram? Well, here, we have linked support, right? This is an example of linked support. So going to the diagram, here we have the 2 premises that support the conclusion, 1 and 2. You'll probably figure this out already, but what we're going to do in order to show that we need both 1 and 2 in order to get 3 is we are going to add a plus sign and then a bracket to show that these 2 need to be together in order to arrive at 3. Okay, so here's another argument that uses linked support. This is the highly original, all men are mortal, Socrates is man, therefore Socrates is mortal argument that you probably have seen already and will see ad nauseum so long as you're taking a logic class put forward by the philosophy department. But if you look at this argument closely, you can see that it's a linked support, right? So it'll look something like this, where the bracket and the plus sign represent the link between 1 and 2 to get to 3. And if you look at this closely, you'll see that neither 1 by itself supports 3, nor 2 by itself supports 3. Right? So just because all men are mortal, if we were to eliminate 2 and just say all men are mortal, therefore Socrates is mortal, that does not necessarily follow, because without 2, it's possible that Socrates is not a man, but a god, right? And if Socrates was a god, then it doesn't follow. It wouldn't be true that he is mortal, right? The same thing is true for 2 as well. If we were to eliminate 1 and just take 2 by itself, 2 does not necessarily support 3. Just because Socrates is man, it doesn't necessarily follow that Socrates is mortal, because without 1, it's possible that there are some men that are immortal, right? Only when these 2 are taken together can we get 3. So we have linked support once again. Okay, one more example of an argument that uses linked support here. We have a 3-premise, 1-conclusion argument that supposedly takes place within the context of a car theft. The first premise says that the only car thief suspects in the case are John, Sally, and Mark. John did not do it, Sally did not do it, therefore the car thief must have been Mark. So here we actually have 3 premises that link up together to support the conclusion. So the diagram will look something like this, where 1 plus 2 plus 3, when taken together, and only when taken together, give us 4. Now sometimes I get asked by students, why can't we just arrive at 4 just by 2 and 3 alone? And the reason is because if we don't have 1, that limits the number of suspects to simply John, Sally, or Mark, then it's possible that instead of 3 suspects, we might have 5 suspects or 10 suspects. And if that's the case, then we cannot conclude that the thief must have been Mark simply by eliminating John and Sally from the equation. It's only when we have all 3 of these taken together that we can arrive at 4. So once again, we have a linked support. Okay, so by now you should be familiar with convergent support and how to depict that in a diagram, as well as linked support and how to depict that in a diagram as well. And sometimes I get asked whether it's possible to have an argument that combines both the linked support and convergent support in one diagram. And the answer is, as you probably guessed, absolutely. In fact, the more difficult passages we get into, the more we'll see that there is a combination of these 2 types of support in one argument. And here's an example of an argument that consists both of linked support and convergent support. So we're going to have to depict that accordingly, represent that accordingly in our diagram. Here, actually, I just took the same argument from the previous slide about John, Sally, and Mark, but what I've done is I've added 2 extra premises in order to support the fact that Sally did not do it. So, once again, we have our sub-argument here. So let's just get the base of it. This was from the previous slide where we saw that 1, 2, and 3 link up to 4. But here we have to add in our diagram these extra premises which give support for 3. So 5 says Sally had no motive, and 6 says Sally was out of town. So each of these gives support for 3. Now we have to ask, do these support the 3 independently, or do they need to be linked up in order to support 3? And the answer is the former, right? 5 by itself, the fact that she had no motive, supports 3, right? And 6 by itself, that is, she was out of town, supports 3. So we would represent that in our diagram as follows. 5 independently supports 3, and 6 independently supports 3, which is a convergent support. So here, as you see, this is an argument, a diagram of an argument that has both convergent support as depicted here, as well as linked support as depicted here. Okay, now when I say that it's possible to have a combination of 2 different types of support, I sometimes get asked, well, on the exam or in our homework, how are we supposed to label this? Are we supposed to label it as linked and convergent support, or linvergent, or convinct, or how and the answer is really it doesn't matter. The labeling of the argument as convergent support or linked support or a combination thereof really is not what I'm going for. What I'm going for is simply that you accurately depict or portray the diagram of the argument. In fact, so long as you depict the diagram correctly, you don't even have to label the different types of support. Okay, so just to wrap up, we introduced just the basic idea of diagram. We saw how premises and conclusions are represented as encircled numbers, while inferences are represented by arrows. We also looked at two types of support, convergent support and linked support, and we saw how each of those types of support are depicted in a diagram. So I want to leave you actually with one more argument that combines the two types of support. And this argument is actually the most complex one in this current lecture. And here it is. ABC is a right triangle, so the hypotenuse squared is equal to a squared plus b squared, which is the Pythagorean theorem. John measured the side A and got 3. Sally also measured the side A and got 3. So A is 3. We also know that B is 4, so it must be that C is 5. Therefore, the hypotenuse of a triangle, A, is an odd number. So I encourage you to try to diagram this argument using all of the tools that we've learned in this lecture. And I'll wait about 10 seconds, which is not enough time for you to diagram it, but if you would like, and I strongly encourage you to do this, is pause the video and just take a pen or a pencil and paper and try to diagram this. I'm just going to wait 10 seconds so you could hit pause, take out a piece of paper. Alright, so in order to diagram this, we first locate the conclusion, which is 8, the hypotenuse of the triangle. A, B, and C is an odd number, and then we try to go step by step through the rest of these. So let's first start off with 1 and 2. So A is a right triangle, so the hypotenuse squared is equal to a squared plus b squared. So this is a mini sub-argument. 1 supports 2, which we will represent as follows. We also see that John measured the A side and Sally measured the A side and got 3, so we know that A equals 3, which is represented by this, right? We see that John measuring the A side supports by itself that A equals 3, right? And Sally measuring the A side by itself supports 5, that A equals 3. So we have a convergent support here, right? Each premise independently supports the sub-conclusion. Then we have 6, that B equals 4, and there are no sub-arguments for 6. 6 stands on its own. And then we see that 2, 5, and 6, 2, 5, and 6 supports 7. C equals 5. The hypotenuse equals 5. Now the question is whether 2, 5, and 6 support 7 independently, or whether they need to be taken together as a linked support to support 7. And the answer is, of course, they need to be linked together in order to support 7. Only when 2, 5, and 6, when taken together, support 7. And once we have 7, we get 8. So this is what the diagram looks like for this argument. Once again, as you can see, we have a combination of convergent support as well as linked support over here. Okay, so as we go on, you'll start to see these passages get a little bit more lengthy and complex, but once again, we already have the tools that are needed to diagram any argument, at least in theory. So thank you very much for tuning in, and I will see you in class.